The performance of LISA could be severely affected by force glitches acting directly onto the test mass displacement. Here we investigate about the many glitches that have been measured on LISA Pathfinder, and in particular we analyze the possibility of outgassing bursts. My name is Lorenzo Sala and I'm currently doing my PhD at the University of Trento in the LISA group. The LISA Pathfinder mission has revealed several glitches as spikes in the differential acceleration between the two test masses. From the analysis of these events, it turned out that the real forces moving one test mass along the laser-sensitive axis that are sometimes measurable by both the interferometric readout and the capacitive sensor, but most of the times only measurable by the more sensitive interferometer. Many sources have been analyzed, but the real nature of glitches is still not known. Glitches carry no torque, they're just translations along the laser axis and show a wide range of durations. Glitches happen with Poissonian arrival timing and therefore are completely uncorrelated. And one key point that is somehow weird is that the glitch rate strongly increased during 4 particular noise runs, in which the temperature was lowered to 0 degrees Celsius. The rate increased from nearly 1 event per day to nearly 36 events per day. Glitches appear in two slightly different shapes. The first one is one-sided, either positive or negative, and the second one is two-sided. The most important case is the first one, since it gathers most of the events and has the widest duration time range from few seconds to some hours, with amplitudes ranging from some femtometers per second to hundreds of picometers per second. The key question is, of course, to find a single physical phenomenon that agrees with all these measured properties. One of the most promising candidates is the outgassing of molecules from tiny pores in the structure, such as uncoded parts or cable harnesses. This would agree with the wide range of duration times due to the different sizes of the pores and the no torque property, since particles would enter the electrode housing only through small holes along the laser axis. The rate increase when lowering temperature would be explained as mechanical stresses acting on the structure. We do have a first candidate, that is the internal balance mass, the IBM, that was used to compensate for the self-induced gravitational forces of the spacecraft itself. And as you can see in this SEM scan of a sphere model, the IBM had many pores, the black spots, that might store small quantities of gas. To analyze the pressure response to gas bursts in the very complicated geometry of the vacuum enclosures of LISA Pathfinder, we use this software, MolFlow Plus, that allows to simulate the time evolution of pressure on faces, in our case on the two main faces of the test mass, the faces along the laser axis. We simulate the differential pressure as the response function to gas bursts, and then convolution with the outgassing profile leads to the pressure profile, and then of course to the differential acceleration profile. And so we run simulations. This is an example of a simulation with the real design of the LISA Pathfinder mission, with particles emitted from the front side of the IBM. It turns out that few nanograms of water would be enough to generate the average 1 picometer per second glitch. The long duration of some glitches requires a slow outgassing mechanism from the pores, since the lifetime of particles in the vacuum enclosure is very short and is not enough to explain long-lasting events. As you can see in this histogram, the lifetime is less than a second against the hours of some glitches. And this is the result of the simulation on the right, made with 1 million virtual particles emitted from the front side of the IBM. As you can see as a blue line, this gives a strong differential pressure in the positive direction that is of course proportional to the force applied to the test mass. Explaining two-sided events is somehow trickier. Timescales are shorter than glitch durations, and pileup is too unlikely to be the reason. Fortunately, there is still a chance for outgassing. The only explanation from this perspective would be a double-sided response function with an integral close to zero, and thanks to the properties of the convolution, the response function would behave as a differentiator on the outgassing profile, allowing for double-sidedness. The problem is that it is very hard to find spots in the geometry that produce such a push and pull pressure, and comparison to glitch properties requires some more precision from simulation, and we are planning to go deeper into this topic. We are also planning to run on-ground experiments with the high sensitivity torsion pendulums at the University of Trento. Given the noise spectral densities and the LISA Pathfinder glitch template to match, it is possible to evaluate the signal-to-noise ratio for both the 1 test mass and the 4 test masses pendulums, and evaluate the detectability thresholds to compare with the real events. As you can see in the figure on the right, triangles and histograms represent measure properties, and solid lines represent thresholds corresponding to different noise levels. Of course, the quantity that is measured by torsion pendulum is the torque that has to be converted to the equivalent acceleration of LISA Pathfinder. And dedicated experiments are necessary to study the real-time profile of gas bursts and therefore to study the impact on LISA. In conclusion, force glitches on LISA Pathfinder have been analyzed as due to pressure bursts in the vacuum enclosures, running simulations with the real geometry design. Small amounts of outgassing water of the order of nanograms could produce the picometers per second of one-sided glitches measured on LISA Pathfinder, and we are planning to run on-ground experiments to go deeper into this analysis and to study the impact on LISA of these pressure bursts. And thank you for listening, and thank you for your attention.